continue talking about acids and bases today. You already have most of the learning goal mastered because you quizzed out, and we'll share those quiz grades with you. Our focus today is going to be on neutralization reactions and titration, and you'll be titrating in the lab this week. Definitely one of the coolest labs. With titration, we can figure out the concentration of a substance, in this case, an acid or a base. And so by the end today, you should be able to understand titration as well as do the calculations involved with titration problems of an acid and a base. We're going to pick up with neutralization reactions. You already know how to predict products of a neutralization reaction. You probably just didn't realize that they are neutralization reactions. These are going to be double replacement reactions. We're going to react an Arrhenius acid with an Arrhenius base. Remember, an Arrhenius acid generates protons, an Arrhenius base generates hydroxide ions. You'll recognize the Arrhenius base right away because you will have some metallic cation and hydroxide ion here. When you react an Arrhenius acid with an Arrhenius base, you always get a salt that's going to come from the insides and water. So these are double replacement reactions where you put the outsides together and the insides. Your products will always be salt and water. The salt has different properties than the Arrhenius acid or the Arrhenius base. Remember, acids have pHs less than 7. Bases have pHs greater than 7. Salts typically run in the neutral range, although you can get them being slightly acidic or basic. Your other product will be water. So the salt will have different properties than the acid or the base. You, of course, would never taste something you generated in the lab, but if you did, your solution would be salty, and it wouldn't react with metals the same way that acids do. Here's an example of a neutralization reaction, and again, this is why it's important that you know how to write chemical formulas for acids and bases in order to predict products of a neutralization reaction. You've got hydrochloric acid reacting with potassium hydroxide to generate potassium chloride and water. So the inside, there's the salt, potassium chloride. Make sure you write the metallic cation first. The other product's always water. So looking here, let's predict products of the following neutralization reactions. They're neutralization reactions because you generate neutral products from acids and bases. I'm going to flip screens for a minute because I have this written out a little bit larger. In the first one, which is done for you, you have sulfuric acid reacting with magnesium hydroxide. You get magnesium sulfate, and don't get confused here, the other product is always water, OH, which is H2O, and then you balance it accordingly. So for example, sulfuric acid and sodium hydroxide, you're going to put the insides and the outsides together. Here's the inside. You've got sodium sulfite and water. So you always get a salt, hence neutralization, and water. And when you go to balance it, just watch these H's now. You've got 2 sodium on the right. You'll need a coefficient of 2 here. That makes 2 H's here, 2 H's here for a total of 4 H's. So you need the 2 in front of the water. And again, these are just double replacement reactions, nothing different than what you learned earlier in the year. Insides to get the salt, you've got potassium phosphite, and what's your other product? When you go to balance, you have 3 potassium, so you need 3 potassium hydroxide here. You have 3 H's, and 3 H's is a total of 6, so you need the coefficient of 3 here. What would be the products of hydroiodic acid and calcium hydroxide? Your salt is calcium iodide, correctly formula written. Your other product is always water. You need 2 I's on both sides, and then you have 4 H's on the left, a 2 here. What would be the product of this neutralization reaction? Yep. And always water. So you would need a coefficient of what here?
2.
And a coefficient of 2. The only way you can make this a little bit sneakier if you wanted to would be in the following, where these, you've got names of acids, and again, you should have mastered naming at this point. You were quizzed on it. Hydrochloric acid, make sure that L is lowercase, reacts with barium hydroxide to generate barium chloride, correctly formula written, and H2O. 2 chlorines on the right, so you need 2 on the left, and 2 water molecules. What about perchloric acid? So HClO4, calcium hydroxide. What would you make? Cation first, calcium. What's missing?
2.
Correct? So you need a coefficient of 2 and a coefficient of 2. And one of the first steps in doing these titration problems out on paper is writing the correct neutralization reaction out. And you'll get a little practice with this in your classwork. Just be careful. I gave you a section in your classwork where I give you reactants only, and you have to predict products. Whenever you see hydroxide ion, it's going to be a neutralization reaction. If you don't, it's going to be a conjugate type reaction that you learned about previously. So the presence of a hydroxide ion will signal you that it's a neutralization reaction where you're generating a salt, which is typically in the neutral range, and water. So those are your neutralization reactions. Questions? Sometimes acids can donate more than 1 proton. If that's true, these acids are referred to as polyprotic acids, and you won't see complete neutralization of polyprotic acids until all of the protons have been donated. We're not really going to get into this at this level. I did show you monodi and triprotic, but for example, if you had chlorous acid, it is a weak acid, equilibrium lies far to the left. This is a weak acid, and this weak acid is monoprotic, 1 ionizable proton, as opposed to sulfurous acid, which is diprotic, 2 ionizable protons. And in this case, what happens is that your conjugate base can then act as an acid, continuing to donate 1 proton. So this is a weak acid as well. This is diprotic. Phosphorus acid would be triprotic. It has 3 ionizable protons. So this would occur as such, and then this substance could act as an acid as well. again, equilibrium far to the left. These are weak acids, so this is the triprotic. And the only thing I want you to see is that this substance and this substance are considered polyprotic acids. More than one ionizable proton. Other than that, you don't really know. Di versus tri, you already understood that. And you'll get into more of that in college chem. We're not going to worry about it at this level. The naming of salts you already know how to do, and I showed you the relationship between ate and ick on the acid and ite and OUS. So we're going to skip this section. You're welcome to look through it, but you already know it. And we're going to pick up today at titration. And titration is a very useful procedure that you can do to determine the concentration of an acid or a base. And truthfully, when you get into more advanced chemistry, you actually can do redox titration, where you've got oxidation reduction reactions, and you can figure out concentrations of substances. For our purposes, we're going to be able to determine concentration or volume of a solution that is acidic or basic. And shown on the right here is your setup, and this is what you're going to be doing in the lab. You'll have a long, skinny glass tube, and you'll see several of them around the room because we've been setting up for this. And I'll go through how to do the titration tomorrow when we actually perform it in the lab. It's very fun. At first it's a little bit challenging, but just like everything else with practice, you'll master it, and it's very, very fun. I think you'll get a kick out of it. I always laugh because kids get so excited over the faintest color of pink. You'll see it's clear, it's pink, you shake it up, it's clear, and then eventually you'll just get this faint color that remains. This video will show you a little bit about the ins and outs of titration. I'll go through titration with you in more detail tomorrow, the actual procedure. Today I'm going to focus more on the calculations. A lot of what's in the video is written down, so that'll make it a little easier for you. We'll take a look at this video here.
The burette, used to precisely dispense a measurable volume of titrant into an element solution in a titration, until the end point of the reaction is reached. The right hand is used to swirl the flask, while the left hand controls the stopcock from behind the burette. Rotate the stopcock with your thumb, pointer, and middle fingers. This allows better control for delivering partial drops.
And again, this takes a little bit of practice. This is your burette, and I'll teach you how to use it. The solution that goes into the burette is the titrant, and the solution that's underneath the burette that you're titrating into is called the analyte. And she talked about that stopcock that controls the flow of titrant from the burette into your analyte.
Check to see if the burette is clean by rinsing with water and noting any beads on the walls.
So if it's like this, it's dirty.
Make sure the stopcock is closed.
And that'll be really important. The stopcock is closed when it's parallel with the bench top. When it's perpendicular to the bench top, it's open, and the titrant will just flow through.
Bring the burette down below eye level. Use a funnel to add small portions of titrant for rinsing.
And we'll go over how to clean the burette.
Wet all areas of the burette with your titrant by rotating horizontally and drain out through the stopcock. Drain all rinses completely. Repeat this 3 times to ensure all contaminants are out. Fill the burette above the 0 mark with your titrant. Pour with the burette below eye level. Pour slowly so the burette does not overflow. Remove the funnel after filling. Check for bubbles in the burette, especially in the tip. Bubbles will cause significant errors in volume. To remove any bubbles, quickly move the stopcock back and forth. zero mark to eye level to avoid parallax, and drain slowly to the zero mark or below. Remove any hanging drops from the tip of the burette by touching it to a clean glass surface. Any drops are considered delivered volume. Record the initial volume by using a card with a dark line. This helps darken the meniscus curve for better reading. Read it to 2 decimal places. Add 2 to 3 drops of indicator to your analyte.
And we'll be using phenolphthalein, which is an indicator. It'll be clear in acid, but pink in base.
It is wise to do a rough titration to determine the relative volume needed to reach the endpoint. Place the flask under the burette on a white background. The color change will be more noticeable. Adjust the burette so the tip is inside your flask to avoid loss of titrant.
And now you're seeing some pink in there.
Titrate rapidly at first, with constant swirling. As the endpoint approaches, the color will be more persistent. Slow the drops down to 1 per second. Touch the tip to the sides of the flask and wash the sides down with water so that all titrant that has been delivered has reacted. Slowly open the stopcock and allow a partial drop to form. A partial drop just covers the tip of the burette. Touch the tip and rinse until the endpoint is reached. The endpoint is noted by a faint color that is persistent for at least 10 seconds, but not permanent. Obtain a final reading. The volume titrated is the difference between the initial and final reading. The concentration of your analyte can now be calculated. Let's review the steps. Make sure the burette is clean. Rinse 3 times with small portions of titrant. Fill the burette with titrant to above the 0 mark. Remove any bubbles. Drain to 0 or below. Take initial reading. Add indicator to analyte. Titrate quickly at first, then drop per second. Touch tip and wash sides of flask. Add partial drops and wash sides until endpoint is reached. Take final reading. Calculate your concentration.
And that's what I'm going to show you right now. And again, we'll illustrate the titration very slowly when we go to do it. But the video does give you some key insight into a few terms. As I mentioned, the solution in the burette is the titrant. The other solution in the Erlenmeyer flask will be the analyte. When the color change occurs, that's the end point. If you don't get a color change, chances are you forgot to put the indicator in. At the equivalence point, which will match the endpoint, but endpoint signals color change, or I guess color change signals endpoint, may be stated more properly. The equivalence point is when moles of acid and base are stoichiometrically equivalent, and we'll talk about that. For example, if you do a titration with hydrochloric acid and sodium hydroxide, initially you will have indicator in the acid and it will be clear. When you add just enough base to neutralize all the acid, you will be at the equivalence point, which will be signaled by the endpoint, the color change. If you add more base than you have acid, then you will be past the equivalence point with a pinkish or dark pink color. What we want to really focus on today is how to calculate concentration or volume of an acid or a base, and it's typically a 4-step process. Few tricks I want to show you along the way, and then we'll walk through 3 examples. so that you understand this type of calculation that you'll be assessed on both in the lab and on the test. First step is always to write your balanced equation. This is your neutralization reaction, and that's why we went over neutralization reactions initially. You also want to indicate the information that is provided about each substance, and I'll show you how to set that up. You'll then calculate moles or millimoles of the acid or base, whichever substance you know both the concentration and the volume of. You will calculate the moles or millimoles of that substance first. And let me remind you, in regard to molarity, you know, for example, that molarity is equal to moles of substance over the volume of solution in liters. So, for example, if you wanted to know the concentration of acid, you'd have the moles of acid over the volume of acid in liters. Well, if the volume is given to you in mils, sometimes it is easier to look for millimoles of acid instead of moles. So one calculation that will be very useful to you is millimoles of acid is equal to the concentration of the acid, that is the molarity, times the volume of the acid in mils. And so we're going to introduce a new unit, if you will, millimoles. You've seen it before, but we haven't done much with it. If your volume is small and in mils, it's much easier to get millimoles as opposed to moles, because you don't have to start converting and converting back. It's just not worth it. Same thing for the base. So this is going to be millimoles of acid or base. And you'll see where that comes into play in just a few minutes. Whichever one you know both the concentration and the volume of, you'll get first. You can get the other one by stoichiometry from the balanced equation, and that'll be step C. And then finally, you'll calculate the concentration or the volume, whatever it is they're asking for. So a 4-step procedure. I'm going to label the steps as we go through A through D to make it a little bit easier for you. You don't have to label it when you do the problem. I just want you to have a guideline in case you're working through and you're having difficulty following. We're going to walk through 3 examples. In the first example, it says in a titration of a sample of 20 mils of hydrochloric acid, we have 20 mils of acid. 30 mils of 0.2 molar sodium hydroxide is required for neutralization. Then we want to calculate the concentration of the acid at the equivalence point. The equivalence point is where moles of acid and base are stoichiometrically equivalent. First thing I'm going to do is write the neutralization reaction. So 1A, I've got hydrochloric acid reacting with sodium hydroxide, double replacement, insides, other product, water, and that is balanced already. The other thing I like to do is I do prefer to put all the information down. The volume of the acid is 20 mils. The volume of the base is 30 mils. Concentration of the base is 0.2 molar. I'm looking for the concentration of the acid, and again, those brackets mean concentration, as we've talked about this whole 9 weeks. first thing I'm going to do is get millimoles of the acid or the base, whatever I have both the concentration and the volume of. In this case, sodium hydroxide. So I'm going to get millimoles of the base by multiplying the concentration times the volume. And for a lot of these problems, you don't even need a calculator. This is essentially 2 times 3 is 6 millimoles of sodium hydroxide. In step C, I'll take that quantity, and from the balanced chemical equation, I can do a very simple mole or millimole ratio to get the millimoles of hydrochloric acid. I've got 1 millimole of sodium hydroxide, 1 millimole of hydrochloric acid, so I have 6 millimoles of HCl. Here's my stoichiometry at the equivalence point. I know the millimoles are stoichiometrically equivalent. And then finally, in the last step, I want to get the concentration of HCl, that is the molarity. I've got 6 millimoles of HCl, and I will divide it by the volume of HCl. 6 over 20 is the same as 3 over 10, so my concentration is 0.300 molar HCl. So from the information provided and through following steps of a titration problem, I can calculate the concentration of the acid in this case. And if you follow these 4 steps, you'll be golden with these types of problems. So that's the first example, which was relatively straightforward because of the 1-to-1 mole ratio of acid and base. Your titration in the lab will be sulfuric acid with sodium hydroxide. The only difference in the lab is you may not know the volume of the base straight up. That will be red on your burette from where you started to where you finished at the equivalence point, which would be signaled by the end point. Let's take a look at number 2. On number 2, it says in a titration of a sample of 1.5 molar calcium hydroxide, is that the acid or the base? Base. 25 mils of 0.8 molar hydrobromic acid. That's your acid is required for neutralization. Calculate the volume of the base. So this one is ever so slightly different. They ask you to calculate the volume, which is a little unusual, but it's done very similarly. Steps A, B, and C will be identical. So the first thing we want to do is write the balanced chemical equation. We've got, I always write the acid first. You don't have to. It's probably just how I learned 100 years ago, so it's easy for me. Hydrobromic acid reacting with calcium hydroxide. Again, neutralization reaction is a double replacement reaction. We're going to generate calcium bromide and water. Balance, balance. The concentration of the base is 1.50 molar. I want to figure out its volume. The concentration of the acid is 0.8 molar. the volume is 25 mils. So in this case, do I want to get millimoles of the acid or the base first? Acid, because I know both the concentration and the volume. So you're just going to multiply here. And step B can lead right into step C if you don't want to write it down twice. So we have 20 millimoles of hydrobromic acid for every 1 mole of base. We have 2, and this really you would want millimoles. So you have 10 millimoles of calcium hydroxide. So B and C are built in there. And then on D, don't let this be confusing to you. You know that molarity is millimoles over the volume in mils. So if they ask for volume, you know how to interchange a numerator on one side of the equation with a denominator on the other side. So the volume in mils would just be 10 millimoles over, this is a base, so in this case the concentration, and you would have 6.67 mils of base. And it's not that common to ask for mils. Typically they ask for concentration, although truthfully it's done the same way, so it's not a biggie. So again, write down the balanced equation and neutralization reaction. Write down the information provided. You'll get millimoles of the substance. You know both the concentration and the volume. You simply multiply the two. Using a millimole ratio, stoichiometrically, you can go from one substance to another, and then you'll divide either by the volume or the concentration, depending on what they're asking for. Question 3 is very similar, but I've put 2 additional questions in it that requires mastery of stoichiometry, which all of you had back in January. It's just been a little while, so we need to just wake up those mastery skills and then make sure you can apply it here. And you'll see some of this on your semester exam, so the review process will just kick in right here, which is good. On number 3, it says, in a titration of a sample of vinegar, 11.10 mils of 0.748 molar strontium hydroxide, is that the acid or the base? Base. Is required to neutralize a 10 ml sample of vinegar. Vinegar is serving as the acid. Vinegar contains acetic acid. And we want to determine, I usually put my unknown in yellow, so let's go blue here. Calculate the concentration of the acetic acid in this sample of vinegar at the equivalence point. There are 2 additional questions. We'll get there in a little bit. But you already know theoretical yield and percent yield. It's just a matter of linking it back here, which we will help you do. So on number 3, and this one might look a little funny because acetic acid is your ionizable protons in the back, so that may be a little tricky to you. I won't give you one like this on the test, but some years we run multiple titrations, and the second titration lab I like to do has acetic acid in it, so I like to go through this example. So we've got acetic acid, CH3COOH. reacting with strontium hydroxide. So here's the ionizable proton that you get the water from, and your other product is strontium acetate. We want to know the concentration of the acetic acid. The volume of acetic acid is 10 mils. Concentration of strontium hydroxide is 0.748 molar, and the volume is 11.10 mils. So that's the first step. And what are you going to get millimoles of in this problem? Why must you get millimoles of the base first? Because you have them both. Good. So we can multiply these. And that's going to be 8.30 millimoles of strontium hydroxide. How can we get millimoles of the acid? Yep. Stoichiometry, millimole ratio. For every 2 millimoles of acetic acid, you have 1 millimole of strontium hydroxide. So that'd be 16.6. And then how do you get the concentration of acetic acid? You have millimoles, right?
Divide by volume.
What volume?
10.9.
Yeah. And there are 2 additional questions that were asked. The next one was the theoretical yield of the salt. What salt forms? If it's a yield, is it a reactant or a product? Product. So what's the salt? Strontium acetate, right? Because the other substance is water. How do you get theoretical yield of something? What do you always start with?
Actual.
Careful.
Percent theoretical.
Careful. Starts with an L. Limiting reagent. Now, looking at your problem earlier, you had this many moles of strontium hydroxide and this many millimoles of strontium hydroxide and millimoles of acetic acid. Are these stoichiometrically equivalent? Yes. So you can use whichever one you want with one little alteration. I typically will go back to this before I did the stoichiometry. Now this is millimoles, and you're ultimately going to want grams. So you really want this in moles. You move the decimal 3 to the left, or divide by 1,000, or multiply by 10 to the negative third. It's all the same. So if you had 8.30 times 10 to the negative third moles of strontium hydroxide in 2 steps, can you get to the theoretical yield? Sure you can. You already know how to do this. It's just a matter of remembering. So from the balanced equation, which I'm going to pull down so you can see it, for every 1 mole of strontium hydroxide, you have 1 mole of salt. And for every 1 mole of salt, you can get grams from the periodic table. So formula mass 205.7074. And that's 1.71. So some of you may want to scribble a little note in your notes. You can use moles of either the base or the acid. It doesn't matter which, because they're stoichiometrically equivalent. Just make sure that you go from millimoles to moles, and all you have to do there is multiply by 10 to the negative third to go from millimoles to moles. Once you have that, you'll have your mole ratio from the balanced chemical equation, and then you have your mole to mass conversion as you learned earlier in the year. This is your theoretical yield. This is how much salt you should be able to generate in a perfect world. The last question in this problem asks what the actual yield is. They tell you the percent yield is 80, and they want to know the actual yield. The actual yield is how much you generate in the laboratory. You know back from a previous chapter that the percent yield is equal to the actual yield over the theoretical yield times 100. So if you wanted to know the actual yield, that's the percent yield over 100 times the theoretical yield. So that would be 0.800 times 1.71 grams. And this should look very familiar to you. That's a 7. 1.37 grams is your actual yield. Some of you may need quite a few problems on this to get the juices flowing from earlier in the year, and you'll find this on your classwork. There's one other piece I want to show you in your notes. We did it already. It's just a good review. On your classwork, you now can do page 2 on both classworks, and I would recommend some greater understanding for these types of problems prior to your lab. Your lab will run for 2 days, and then we'll have a problem-solving day built in as well. You won't test out until next week, because I know you have a lot going on at the end of the week. The last thing I want to mention to you, we already talked about this earlier, Strong acids and bases ionize completely. So for example, if you had hydrochloric acid, it ionizes completely such that the concentration of hydrochloric acid and hydronium ion is the same. For a weak acid, that's not the case. You can see this reversible reaction with equilibrium lying far to the left. So with a weak acid, the concentration is not equal to the hydronium ion concentration. We find that the concentration of the weak acid is significantly greater than the hydronium or proton. So you calculate pH for a weak acid very differently. If you want to learn how to do that in small groups, I'd be more than happy to show you. With a strong base, again, as we said previously, it ionizes completely, and that strong group 1 base has the same concentration as the hydroxide ions. Be careful with the strong group 2 base. That's a little different. With a weak base, these concentrations are not the same. In regard to your strong acids, 3 of them are binary: hydrochloric, hydrobromic, hydroiodic, all strong. Hydrofluoric is weak. Common mistake kids make. For ternary acids, it's typically strong if you have at least 2 more O's than you have H's. It doesn't always work. We mentioned polyprotic acids already, and we talked about strong bases. Be careful with those strong group 2 bases: calcium, strontium, and barium hydroxide. For those of you who want to learn how to calculate pH for weak acids or bases, that's a little more complicated. I'd be more than happy to show you separately. And the last piece of information I want to leave you with is this reversible reaction right here. You have carbonic acid, equilibrium reaction with water and CO2. Looking at that equilibrium reaction here, if you are really, really uptight and you are hyperventilating, what do they tell you to do? Breathe into a paper bag. Exactly. So, what gas are you exhaling when you breathe? Carbon dioxide. So if you breathe into a paper bag, you drive up the concentration of CO2. You've trapped it in the bag. And now equilibrium will shift to the left. So equilibrium will shift to the left in an effort to use up all that CO2 that you are exhaling. And that will slow you down and hopefully get your breathing in a more normal rhythm so that you're taking in oxygen and releasing CO2. So equilibrium can greatly affect you. If you've ever needed a paper bag to stop hyperventilating, that's the reason right there. In regard to titration, make sure you know those steps like the back of your hand. You will see titration big time on your test. In addition, you're going to be doing the lab. Make sure you understand the indicators, what colors things change, because a lot of what we do in the lab you will see on the test as well. Questions here? So you want to be able to do both page 2s of your classwork to make sure you understand titration. Theoretical yield, again, either substance can be used because there's no limiting reagent per se, and actual yield.